Okay, this is Solutions 2, and it is the second video in the Solutions unit, and it's all about solubility. So, what kind of things can dissolve in what? How much of it can dissolve? What are some things that we can do to make things dissolve better, faster, stronger? Hope you got that reference. So, we're going to start off by actually defining solubility. Solubility is the ability to dissolve or be soluble in something, right? So it's officially defined as the amount of a substance that a solvent can hold at a certain temperature. Okay, and then we call that a saturated solution. So what we do is we take like a set amount of liquid, so like 100 milliliters of water as our solvent, and we dissolve salt or whatever our solute is until it can hold no more. And then at that point where it holds no more, that is a saturated solution, and then we write that number of grams down, and that's our solubility. So for example, if I can dissolve 23 grams of salt before it won't take anymore, in 100 milliliters, then the solubility is 23 grams of salt per 100 grams of water. Great. So let's go to the idea of a saturated solution. Okay. Oh, too much. Is a solution that will contain the maximum amount of the dissolved substance. Okay. So if you can put in all 23 grams, that is a saturated solution. It contains the maximum amount that it can hold. That's saturated. And so, of course, if it is unsaturated, then that means it will be less. So that means if you're dissolving salt, it's unsaturated as you're dissolving more and more salt until you reach the maximum, and then it's saturated. So what we find, though, even is that if you heat it up higher, you can dissolve more in it than you could before, right? Like if you have hot tea, you can dissolve a lot more sugar than if you have cold tea. So then if you can dissolve more than the maximum, that is called a supersaturated solution. Okay? Like sweet tea. Sweet tea is a supersaturated solution because when you go to Chicken Express and you get your glass of sweet tea, there's no way that you could dissolve that much sugar in cold iced tea. They had to heat it up, dissolve it, and then cool it back down. And when you cool it back down, then you are tricking it into dissolving more than it should hold at that temperature. Okay? So a supersaturated solution can stay over dissolved like that even after you cool it. But often if you shake it or disturb it or drop in some more crystals of the solute, then it will come out of solution, as we will say. And so crystals will begin to form and keep growing until everything is undissolved at that temperature. So we're going to see an example of this, and it can be pretty cool. So what exactly is going on? Well, when we dissolve something. And as budding chemists, we need to know what is going on at the molecular level when we dissolve something. When you throw sugar in water, what is happening on the molecular level with all the little molecules and atoms? So here's a picture of a salt crystal, right? This is the crystal lattice and little structure. And then what happens is when we put that in water, all the water molecules start attacking it. And the important thing to note in this is that this happens because of water's molecular structure. Remember, in the last unit, we talked about water being a polar molecule because it has a positive end and a negative end. The oxygen in water contains the negative charge, partial negative charge, because of the electrons that reside on the oxygen. Okay? And that partial negative is what attracts the positive sodium ion, because negative attracts positive. So that's why over here on the sodium, you see, hold on, let me try something. Okay, so over here, you have the sodium positive being attracted by little negative oxygens. I'm going to change my pen color to something a little funner, like red. So over here, you see that the positive sodium is being attracted by the negative oxygen ends, okay? And then hydrogen has a partial positive charge. And so you see that the hydrogens over here, because they're positive, attack the negative chlorine and kind of surround it like bullies. And so that's why sodium and chlorine can't bond anymore like they are over here, because they are separated by water, kind of like as little bullies. And that's because of water's molecular structure, being that it's polar. So now we're going to talk about the rate of dissolving. So how fast can you dissolve something? So let's say you're given a sugar cube and a little bit of water, and I tell you, you have to dissolve this as fast as you can. Ready, go. So what are some things that you're going to do to help it dissolve? Are you just going to throw it in there and watch it? Well, probably not. And so if you think about it, this is what you're probably going to do. You're probably going to grind the cube, right? You're going to smash it up. If you have like a little stirring rod, you're going to smash it up. And grinding the cube, what are you doing? Why is that making it faster? Well, as you're grinding it, you are creating more surface area, which means there's more area available for those water molecules to attack. And so it means you get a faster dissolving rate. Okay? This is why if you need a medication to work really fast, you usually have it delivered in a powder instead of a tablet. So aspirin is like in tablets, but if you want fast-acting aspirin, it usually comes in a capsule filled with powder, because the powder has more surface area. Okay, what else can we do? Well, you probably then with your stirring rod are going to also stir it. That should say stirring, not stirring. Okay, and so again, what is that doing? That is increasing the movement of the particles in the liquid. They're moving faster because I'm stirring it. And that allows then more solvent to dissolve, because again, you're letting more molecules attack those crystals. Okay, then you can also heat it. And again, why would heating work? Well, because you're increasing kinetic energy, and that increases movement, and just like up here, increasing movement helps more water molecules attack it. Okay, it also gives it more energy to break those bonds, because it has more heat energy. So those three things affect the rate of something dissolving. Okay, so now we're going to go on the back to page 3. So what about factors that affect solubility? And remember, solubility is the amount that a liquid can hold. So how many grams of salt can water take before it won't dissolve anymore? So one factor that affects it is that you can only dissolve like things. Like can only dissolve like, and that has to deal with our good friend polarity, right? Polarity. So polar solvents can only dissolve other polar solvents and ionic solutes. Okay, so polar can dissolve polar and ionic things. And that's why water, which is polar, dissolves salt, ionic substances, right? Water dissolves salt, and that's because like dissolves like. Also, that means that nonpolar substances can only dissolve nonpolar substances. So oil, a nonpolar substance, can only dissolve other nonpolar substances. So that's why you can dissolve like butter in oil, but you can't dissolve butter in water, right? Water, which is polar, cannot dissolve oil, which is nonpolar. That's why oil and water separate. Okay? And on your packet, you have two words called miscible and immiscible. And for our purposes, we're going to ignore those. If you really want to know, you can come ask me. That's kind of basically, miscible means that it will always dissolve, and immiscible means it only sometimes dissolves. But anyway. Okay. 2 is pressure. Pressure can also have a substantial effect on things dissolving and how much will dissolve. Okay, for a solid, there is a negligible effect, which means there is almost no effect. If you have a high pressure or a low pressure, it really doesn't matter. Like salt, it doesn't matter whether you are at the bottom of the ocean or you are at the top of Mount Everest. It is not going to affect how much salt can dissolve in water. But Let's say you're dissolving a gas in water, like your soda. Then the solubility of a gas is proportional to the partial pressure of that gas on the surface of the liquid, vapor pressure, right? And that's called Henry's law. So Henry's law says that it's proportional. So what that means is that if you want a gas to stay in a liquid, you have to put a high pressure on it. So think about it. If you had a carbonated soft drink, do you think that having a high pressure in your bottle is going to help it stay, or a low pressure? And obviously it's going to be a high pressure. That's why when you buy a bottle, it has a very high pressure, and then when you open the bottle and make it a low pressure, what happens? A bunch of bubbles come out. The gas no longer can stay dissolved. So we'll talk more about that. Then we also have this idea of effervescence, and that is the rapid escape of a gas from a liquid in which it is dissolved. So like if you shake a can of soda, you have now experienced effervescence, because shaking a can of soda, which is dissolved carbon dioxide, gives you a rapid escape of gas. Those of you that did the Alka-Seltzer lab know this, because if you look on a box of Alka-Seltzers, it says it's called an effervescent, and it will say that on the box, because when you drop it in there, it releases a bunch of gas, and you drop it in water. Okay, and then the last thing that can affect it is temperature, right? And we all know this, because if you need to dissolve something faster, you're going to put it on the stove and heat it up, right? So solids most increase solubility with temperature. So that means usually if you make it hotter, it will dissolve more, as in most will. Okay, so what about gases? Gases do the opposite. If you want a gas to stay dissolved, then you need to make it as cold as possible. Like if I put Coke on the stove, then it's going to all bubble out, and all that carbon dioxide will leave and bubble. So if you want a soda to remain fizzy, you put it in the refrigerator, right? You want it to be cold. So gases, if you want it to dissolve more, then you need to be colder, okay? And so how we relate temperature and solubility, like what we just talked about, that if you heat stuff up, it dissolves more, is through a solubility curve. And the way a solubility curve is, it is solubility on the y-axis, and then temperature on the x-axis. And so this says that as you go up in heat, you can dissolve more. Okay, and this also can tell us our three types, right? Supersaturated, saturated, and unsaturated. If you are on the line, then you are A-okay, and that means you're just plain saturated. If you are above, and that means you have more, then you're supersaturated. And then if you are under and are below, then you are unsaturated, right? Unsaturated is under. Super is above and beyond, like Superman, right? So we can use, this is an example of a solubility graph for like 1, 2, 3, 4, 5, 6 different chemicals, okay? And so we can tell that you have potassium iodide, potassium nitrate, potassium sodium nitrate, sodium chloride, potassium chlorate. So which salt has the smallest change in solubility with changes in temperature? Well, so as you change this, which one is not changing solubility? And remember, solubility is over here. So which one is not changing in this direction, in the y direction, when you go that way? Okay? And so if you think about it and pause the video and decide for yourself before I tell you right now, then it's sodium chloride. Sodium chloride is barely changing as you get hotter, right? It's not really changing this direction, because as you get hotter, the solubility barely changes at all. Okay? So we can ask questions like this, and that's why solubility graphs are really good for us. We can also then just say, okay, so let's say I have water at 75 degrees, and I want to know how much sodium chloride can I dissolve in it. So I'm going to go over here at 75. Here's 75. Follow it up, and then we're right here. Okay? And then if you follow that over here, then you find, oh look, at 75 degrees, I should be able to dissolve 40 grams of salt in 100 centimeters cubed. or 100 milliliters of water. So that is the end of this. So next time in class, we are actually going to be constructing a solubility curve like this for a chemical as a class. So remember to wear your proper lab attire and get ready to have an awesome time, and I will see you then.